Hello friends, welcome. Friends, today's video is going to be pretty interesting because I am going to talk about today the design challenges of implementing a Wi-Fi based system in a IMT spectrum band which is called millimeter wave, 26 gigahertz band. Now friends, you know that operators have purchased huge quantum of spectrum in 26 gigahertz band, and that spectrum currently is lying almost fallow. Operators are thinking of deploying Wi-Fi technology in the 26 gigahertz band instead of using a conventional IMT technology. So friends, in this video, we are going to talk about the challenges. Two fronts. One is the design challenges of designing a CPE to work in the 26 gigahertz band using a Wi-Fi technology, and the amount of implication on the user on the power bill. Because the spec which TEC has released talks about a high power transmission capability on the CPE side, which is as high as 55 dBm. So if you look at this spec, which I'm going to show you here, this is the spec where they are saying 55 dBm on the user premises side. CPE means user premises, which is called the outdoor unit, from where the connections are going to the individual houses where you can connect to your home router. Now, since this is 55 dBm, which is unheard of in any of the conventional IMT technology, it will cause a huge health hazard to the public because of radiation. And I have explained this in this video. Today's video is going to be different because the power levels are so high. It is not only going to cause an health hazard, but it is going to increase your power bill. Means as an individual, you have to pay more electricity. How much you have to pay, what kind of design challenges are there, and why you don't have to pay huge power bills in case of a conventional IMT technology is what we are going to discuss in this video. So this is going to be pretty interesting. So friends, this is the title of this presentation. Pretty long, but pause the video, have a look at it. Who pays the power bill and what are the design challenges to implement an UBR-like system, which is already being implemented in the 5 gigahertz band in the 26 gigahertz band. Okay. Now, before we go into understanding the design challenges and who pays the power bill and how much will be the power requirement, means energy consumption requirement on the user, we need to understand that how the outdoor unit is powered, means how it is getting energy, from where it is getting energy, because there is a base station unit here. If you look at this diagram, this is the link, UBR or LBR. UBR means the conventional 5 gigahertz link. LBR is the 26 gigahertz link where they will deploy the same technology. And this is the CPE part of the outdoor unit. Now, this CPE part of the outdoor unit could have been powered using a separate power device, which is 24/7 on with a backup. But it would have made the system very costly. So they have come out with an intelligent way of powering this device using customer premises equipment. So what they have done, these routers or these devices, which are coming out from this bridge, because what is happening is that how this system is throwing broadband connection to the individual houses. One connection comes out, it goes to the bridge. From the bridge, Cat5 cables will come and go to the individual houses. There will be 7, 8 number of such devices or some cables. You can power maybe 7, 8, 10. I don't know what the number is. But individual houses are connected and getting aggregated here in the Ethernet bridge, which is finally getting aggregated into a single pipe with this link, communicating to the base station, right? So what happens is that you get power from one device here. May not be multiple devices. Is there a scheduler? I do not know. But let's say all the other devices are off. Only you are alive. You power this device. Okay. Now let's say this guy comes up and you switch your device off. Then this guy is going to power the device. Now, what will be the scheduling? Can all the devices power the system at a time? I don't think so. It will be too complicated. But there has to be one guy powering it. Most likely. Therefore, if you are the most unlucky person, you may end up powering the whole device for all the time. But in case of 5 gigahertz, you will not feel the pinch because the power levels are pretty less. Because they may not be transmitting more than 30 dBm or 36 dBm. because they don't need it, and there is a limitation. There is a regulatory limitation in the 5 gigahertz band where you cannot transmit those kind of power. Therefore, the impact in the conventional UBR system because of this design is low. However, if you are going to go for the 26 gigahertz band and you are going to use the same design concept of powering this outdoor unit, you are going to have a hell lot of a problem, both on a design side of this device as well as the total load on the system as far as power levels are concerned. Why? Because of this 55 dBm limit. Why they have placed it? First, there is a health hazard, but why this limit is there is what you are going to know in this presentation. So let's go down to the next slide. Now, what is the design challenges and what drives the power needs? This is important to understand. Now, why do you want a system to be powered to a very high level? What is the purpose? Let's understand this. Let's say if you have a conventional microwave system, and we'll go step by step. This is the antenna port. And how you are feeding this system power? You are feeding it from here. I'm just showing it up. It goes here and comes out, and the antenna port gets powered up. And then there is a telescope here. It's like almost like a telescope which concentrates the overall signal of the RF so that it kind of focuses in a very sharp beam in the forward direction. So unless it gets focused in a sharp beam in the forward direction, you won't be reaching the base station site. You have to reach the base station site, and therefore what you need? You need a very sharp beam, right? Without that, if the beam was too broad, the chances of you reaching the base station will be pretty low because the energy is going to get spread all over the place. So you want the beam to be pretty sharp. Because you want the beam to be sharp, therefore you want the overall system to act like a telescope to focus this energy which you have pushed at this point into a very narrow beam. That's what you need. And that's why you need to push high power. The power you have to push into the overall antenna system is to ensure that this passive antenna system, this whole system which is now acting like a passive antenna system, further enhances the power and pushes the beam to a very sharp, pushes the overall RF signal into a very sharp beam so that it reaches this point where you need it, right? So this is the overall objective, right? So you can achieve this using an active antenna system and a passive antenna system, because there are two ways to sharpen the beam so that the beam becomes very narrow. So what I have done here in this case is I am using a passive antenna system here. This is a passive antenna. This is not an active antenna. Another way to do it is using a active antenna system. This you need to understand what is passive and what is active, right? So this is passive and this is active. Now, in case of an active antenna system, how do you sharpen the beam? You put multiple antennas as an antenna system, and all these antennas you feed current here at different phase angles. When you feed currents in different phase angles, I don't want to get into the physics, it kind of sharpens the beam and makes the beam pretty narrow. So there are two ways now, right? Which is active and this is passive. Now, which one to use? And what is the advantage of using a passive antenna system and what is the advantage of using an active antenna system? And what you should be using is what we are going to discuss and what implication it will have on the user power consumption requirement, means energy consumption requirement. Now, if you are going to use a passive antenna system, which typically you might have noticed, those BTS towers in the GSM days, they deploy these discs where they're transmitting signal in the microwave spectrum, which is very, very high, sometimes 26 gigahertz, 28 gigahertz. These microwave links are already there. So these discs are pretty large. They have to be mounted in a system like this, right? So imagine that if you are going to put a system in the customer premises equipment like this, then the whole system is going to become cost prohibitive. It is not going to be practically feasible to have that flexibility that you have in the current UBR system in the 5 gigahertz band, because you need to put these kind of discs. So it is better to use a system like this. Now, why you don't use such kind of system in case of a 5 gigahertz UBR system, because in 5 gigahertz UBR system, the frequency is low. So therefore, you don't have the challenge. You don't have the challenge to travel at that distance. Whereas in case of 26 gigahertz band system, you have the challenge to travel that distance. And therefore, it is important to have a very focused beam, and therefore you need these kind of disc, the millimeter wave disc, which are already available in the old GSM website, GSM BTS websites. You can already have a look at those sites. Now, you need a beam forming system using multiple antennas. Now, this beam forming system using multiple antennas can prevent you to have these kind of system. Now, it will make the system elegant. And that's why what happens is that in case of 5G FWA system in 26 gigahertz band, you don't have to deploy a passive system. You use active system. Active system ensures that beams are quite sharp using this antenna array system, right? Now, if you are going to use an active antenna system versus a passive antenna system, then what happens? Let's understand the design challenges. Then the power that you are feeding into this system here, this power is equal to the power which gets out from the antenna system. Means, let's say, if you are able to generate a gain of, let's say, 20 dB, right, using a beam forming system like this, right, 20 dB you are able to generate, but you are feeding only 30 dBm power into the system, because this system is able to generate that beam forming, and it is quite elegant and very, very small, versus a system like this, right, where the antenna is quite bulky. So in both cases, you may feed only 30 dBm power into the antenna port, but you will get the same result. But this is less elegant and this is more elegant. So therefore, this is completely ruled out in case of a 5G 26 gigahertz band, the LBR 26 gigahertz band system. You will not deploy a system like this. You will deploy a system like this. But to able to deploy a system like this, you have to ensure that the CPE becomes quite complex. It will be almost like a millimeter wave system, which a conventional 5G system uses. So in order to work around this complexity, you want to use a active plus passive system, most likely. I do not know how they are designing it, but what I believe is they will have an element, they will maybe using some multiple antennas, 2 antennas, 4 antennas, but never going to be 10, 20 antennas or large number of antennas, which you find typically in a 26 gigahertz CPE, right? Here, you will have a 4 antenna system or a 2 antenna system. So you will have some antenna gain, plus you will use some active antenna gain also to able to compensate for the overall loss that you will have if you don't have a 20 or 23 dBi of antenna. Because if this is going to be a 7 dBi antenna gain, then the beam will be very, very broad, and you don't need that. You need the beam to be sharp. Therefore, you need the effect of a 23 dBi kind of a system, and that you can achieve by combining a passive plus active antenna system. Now, how passive and active antenna system impacts the power that you are pushing into the system? For that, you have to go into this Excel sheet to understand what is going on. Now, to read this Excel sheet, friends, you need to go through the assumption first. Now, what are the assumptions? Assumption 1 is PA efficiency. What is PA efficiency? The amount of power that you feed into the system. That is not what you get at the antenna port, because there is a loss of 50 to 60%. Sometimes people say that you get only 40% efficiency. And what is duty cycle? The antenna system may not be on for all the time. It may be on for the 80% of the time, because there will be 10 people working. People may not be working in the night. And this is the cost per kilowatt hour. Now, let's say if you have a power at the antenna port, DVM, right, which includes the antenna gain of 55 dBm, where the passive antenna gain is only 0, then what happens? The total wattage we have already calculated 316 watt. And then if you use these assumptions, you get a watt in the input power, right? This is the total, and it is the power of the antenna port. This is the input power of 506 watts if you use these assumption. And then you can calculate the kilowatt hour on a month basis, which is 364, and your monthly bill is going to be 2,914. You got it? Now, let's say that you have been able to manage with a passive antenna gain of 7 dBi. As I told you that what you will do, you will mix and match, you will do some active and you will do some passive. So assume that you have been able to do a passive antenna gain of 7 dBi, then power at the antenna port requirement becomes 48 dB because it has to add up to 55 dB because that is what the regulation is all about here, 55 dBm, right? So it has to add up total to 55 dB. So 7 dB minus 55 dB is 48 dB. Now the input power at the antenna port is 48 dB. So what would be the input power level at the antenna with the input power level requirement, which will be determined by the PA efficiency and the duty cycle, which will be 63 dBm. Now, the total power at the antenna port will be determined by the PA efficiency, which will be 63 dBm. Then the total input power, assuming PA efficiency and duty cycle in watts, will come out to be 101 watt. And the total kilowatt hour, if you calculate, comes out to be 73, and the total bill comes out to be around 581 rupees per month to the user. You got it now? Now, if I change this to 40%, the efficiency changes to 40%, and the duty cycle remains, you see this number becomes 727. So it depends upon the CPE design. If your CPE design is not efficient enough, your efficiency is poor, then you may get an efficiency of just 40%. Your power bill is going to be much higher, 727 rupees per month, versus very, very small in case of a UBR design, in case of a 5 gigahertz band. And that is substantial. Now, friends, why you have kept this number as 55 dBm? Because you need this margin of 7 dBi at the antenna gain. But if you do not have, because what you're doing, you are mixing and matching of passive as well as active. So you can't keep the passive antenna gain as 23 dBm to have a telescopic effect. That you cannot do because your device is going to become too bulky. So here what you have done is you have basically managed the gain, or system has been designed in such a way that this is going to give you some gain but not that much. And you have to meet all your gain using the active antenna gain. And that is why you need to keep the regulatory power levels at the defined by the TEC as high as 55 dBm, which includes antenna gain. Otherwise, if this number was 50 dBm or 40 dBm, imagine that where you would have gone. You would not be able to manage this antenna dBi because your power levels will be too low. In order for you, the system to have any meaning, means your system would be so poor in 26 gigahertz band, your capability, even if you have a beam which is sharp, your signal strength will be so poor that you will not reach the BTS site. Therefore, in order for you to have these kind of narrow beam, right, reasonably narrow beam, prevent a system like this, which is too bulky, and create a system which is a mix of both passive and active, and have a reasonable power level so that this reaches the base station, you need to keep this power level at very, very high as far as TEC is concerned. Otherwise, what would happen? You will not get this margin of antenna dBi. You will not be able to, if you need 7 dBi, and if you start with, let's say, 50 dBi, then imagine that where you will be. You will be at 43 dBi, you will not have enough power that the system will be able to reach out to the BTS. You understand now why the power levels have been kept very, very high here, 55 dBm. So that's the challenge. There will be an EMF issue, right? That is health hazard issue at 55 dBm. And there will be a challenge that if you don't keep 55 dBm, your CPE design is going to become too complex because you have to have the mix between both active as well as passive. Because if you only rely on active, then this whole system will become pretty complex. And that is what the challenge is, friends, right, with this overall system. So imagine that if you take an assumption, you make an assumption of 40% efficiency and 80% duty cycle, you have to, and then there are some other efficiency, you probably have to pay around 750 to 1,000 rupees. The whole system, the whole UBR system or the LBR system, this system which I showed you here, the number of individuals together have to pay around 750 rupees per month. Now, which one will pay? How they will decide which one will pay? Because the power requirements are definitely going to be higher than the 5 gigahertz band UBR system because of the challenges which I have explained to you, friend. That's what I wanted to discuss in this video, and probably you understand it. And thanks for listening till the end. I'll come back with a new video and a new topic next time. Thank you, friend.